All righty. You guys there? Hello. 23 people. That's pretty good this part of the semester. And people are getting, including myself, for a little bit of fatigue. I don't know, mental fatigue or something. I don't know how you guys are doing. But I do know that the online version of classes can be tiring, people that it's something about it is more effort on everybody's part, I think. From Brandon. Yeah, very tiring. That's my opinion. Somebody might make fun of me and say, "Well, you're old. You're tired anyhow." But I, I say administration people and people who don't teach, they don't understand. They think they look at online and say, "Hey, that's more efficient. That's cheaper. We save on custodial. We don't have to schedule rooms." They look at this thing from a different perspective, where it's all kind of like a business perspective of the product, and. It's more complicated than that. It's just more complicated. Okay. Let me grab my notes. I hope I have them. Okay, before I get going, let's just look at one thing. I'm teaching an algorithms course, and after having done it for a while and gone over the book and stuff, it trained, the material has trained me to look for complexity. If something is happening, you want to know how much information is somehow tied into that. And it occurred to me when I was looking at the binomial distribution. Okay, so X is binomial in P, say. And what is the probability mass function? So notice the count of, let's say we're flipping it, tossing a coin, so P is a half, say. So the count of heads, what is that? What is the formula? So the probability mass would be the function. Okay, so probability of getting exactly I heads in reps of a fair coin is what? It's, then choose I. And then if it's a fair coin, so that would be 1/2 to the I. And then, it's a fair coin, so 1/2 for the tails, n minus I. I know we've been over this a million times, and you've probably seen it a million times, and you're tired of it. But think about this. If you multiply it out, really it boils down to this, and this is just 1/2 to the n. So really, where's the complexity in this? I mean, what makes it interesting? Where's the meat of it? This. Those coefficients, there's complexity in that. It's not a simple thing. I've seen papers, it's not my specialty, but I've seen papers on binomial coefficients and binomial bound, things, bounding binomial coefficients, all sorts of stuff, okay? This is where the complexity is. And in fact, I'm trying to tie this into why the normal distribution is intimately connected to the binomial coefficients. If you draw out the probability mass distribution, what does it look like? So if you draw it out, just really quick here, somewhere along the x-axis, but you get something like this. And of course, we now recognize, you probably should recognize, if n gets larger and p is reasonable, it doesn't have to be 1/2, but it could be, in our textbook, they have 0.7. If n gets larger and you draw out the distribution, it's distinctly normal, okay? But what's normal about it? Well, it's these guys again. So these guys, in a way, they sort of encapsulate the normal distribution. It's like go hand in hand. So, and the normal distribution is not trivial, okay? It has a sort of complicated expression for the density curve here, okay? So, the reason I'm saying this is to tell you that the normal curve is inevitable for several reasons. Last time we talked about repeated measurements, repeated careful measurements. You would get something, this happens, or we took samples. from the uniform distribution. But also, if you're talking about these, you want to understand the binomial coefficients. You've got to, you're going to have to do that with, n could be large, right? N could be 1,000 or something, and you're not going to be. It's very discrete there, right? But when you do calculus and things like that, you need something continuous, a continuous model, and this is like a perfect model for these guys. Okay, that's all I wanted to say. I didn't want to let that go by because we're supposed to do the normal approximation to the binomial, but I just wanted to. This is my perspective, and this is the essence of the binomial, but it's by no means trivial. It's by no means trivial. All right. Okay. So that was one little thing. Let me check are we missing anybody? We got everybody. Everybody's on board here. Okay. So the other thing was, and forgive me for the two classes, the two sections that get out of sync a little bit, and I felt like I needed to give a hypergeometric example. I'm not sure I did. Maybe you should tell me if I did. But
so I'm sorry, I had to go get lunch, get my lunch from the microwave. But so what is this called?
Okay, well, it was kind of a long story, and of course, I'm full of stories, right? I actually knew somebody whose name was Storier, and that guy was full of stories. So anyhow, from a computer science standpoint, I was looking for where the complexity is in the binomial distribution and its mass distribution. Okay, and I took the example of p is a half. So this part just washes out. It's just a scale factor. Okay, so the complexity is in the binomial coefficients, and then I already mentioned this, but if you make if n is fairly large. And
I'm sorry, when you say complexity, what are we referring to?
It's a hard thing to
I'm really sorry.
Complexity usually refers to. Okay, no, that's a legitimate question. It's a legitimate question. Complexity usually refers to how much effort, how many steps, how much time it's going to take to complete something, or to search for something, or to search enough so it's not there. Mm-hmm. This kind of thing is complexity, and the nature of these guys is complex. And I'm making a very roundabout argument here because of the approximation of these numbers by the normal curve. And the normal curve is complicated, right? I mean, it's not a simple function. Mm-hmm. So I'm trying to say that the binomial is the essence of it. That's what's hard to calculate. That's the essence. Are the binomial these coefficients? We figure we learned them in high school. They can't be that complicated. Well, they aren't. To get estimates on the tails of the binomial distribution. That's a non-trivial mathematical exercise. Okay, that's non-trivial.
This is number of steps to do what? To sort these many things.
Okay. Well, I'm speaking loosely, but I mean, what I just said was, if you want to estimate the probability of the tails of the binomial distribution, that's non-trivial stuff, because n could be very large. You could have a lot of these things, and these and n is large. These are complicated expressions. Okay, what are they? I mean, it's like there's a granularity here that is hard for mathematicians, to handle. If you're CS, you can look up in CLRS, the textbook about these tails. Fascinating stuff. Okay, fascinating.
Oh, so that's not I to the power of m, right?
No, that's a binomial coefficient.
Oh, I was looking at that wrong.
Right. So like if you have suppose you toss 20 times and you have a half, and you want to know what's the chance that you get 10, the probability that x equals 10, then what are you going to do here? So it's going to be 20 choose 10, and then it's 1/2 it's a fair coin to the 20, something like that, right? So the key here, the computational thing is this. And I'm telling you, if you don't, it's just there's a lot of them. Okay, maybe one of them you can compute, but then there's a lot of these binomial things, right? if this was like x, if you want x greater than or equal to 10, then you have to do 10 of them. If this was 1,000, then this. What I'm trying to say is this is a non-trivial mathematical exercise to characterize the growth or how what those coefficients are like. This is the essence. And I'm using this complexity thing sort of generally.
I think it's a bit too general for me to understand it.
Well,
like I understand complexity as a concept, but I don't know what we're doing. I don't understand what you're computing.
Suppose you want to get a good bound on the coefficients sitting to the left of this marker right here. Okay, so you have a lot of coefficients. You're adding them up, right? Well, then how do you establish that? How do you get a tight bound on that? Okay, it's tough mathematical problem. How do I know?
Like just the number of items that fall to the left of that.
Well, you want to get a numerical approximation. See, it's like if you want to add up the binomial coefficient to the left of some number, right? So to add those things up, they don't add very well. Okay, that's complicated. It's complicated to do. And I was saying that these coefficients, if you look at the whole picture, it follows a normal curve, and then you can, if you know that approximation is good, and the approximation is good if it's a rule of thumb. If you have it.
Okay, so you're like just talking about adding them up, and so we're now approximating that with calculus with area, basically.
Yeah, but it's a non-trivial exercise.
Okay.
Hold on. Let me look. Let me look first. Let's see.
What function do we use to approximate that with?
It's complicated, but I'm just searching for. Let me.
Okay.
Let me just. Hold on a second. I want to get. So NP times 1 minus P is greater than equal to 10. If this is a good approximation, this normal is a good approximation to the binomial if this rule of thumb is in place, okay? Then you can do these approximations. But remember, we have another approximation for the binomial, and that was the Poisson. But that was slightly different conditions. You had n is large, p is quite small, and np was moderate. Okay, that's a different set of conditions that should be in place. But let me review this I'm worried about getting behind. Let's do the hypergeometric thing here. And let's see if that rings a bell. Maybe I did it already, but.
For what it's worth, we did do an example of the hypergeometric series. We did the one with there were 10 items in a lot, and an inspector is going to inspect 3 of them. That was our hypergeometrics example.
Thank you, and help me. I've got there's been a collision of the two, sections. Because there was a much better example in there. There was a much better example where you had 4 white and 4 black, 8 total. And this example, which I really think is nice, and I just don't remember if I did it for you guys, but if you want to take samples of size 4 in this case, okay? So we're looking at a sample size of 4. So sample size is 4. And the question is, how many draws, how many reps do you have to do, or what would be the probability that it takes, let me get how many reps. It takes 10 reps for you to get a balanced hand of these. So a hand is, in this case, you take 4 of them. And it's balanced if you have 2 white and 2 black. Okay? So, you grab 4 and okay, you got 4 whites or something like that. Throw them back in the urn, and stir up the urn, and then take 4 out again. Do you see the process here? So the question is, how many times do I have to go through that? How many times do I have to iterate that process? Before I'm likely to hit. So the thing that we'll say that suppose it took you 10 times. What's the probability that it took you 10 reps before you got a balanced hand? In other words, 2 white and 2 black in your sample. So how to write that? You want the probability that it takes, takes 10 reps to get the first balanced hand or balanced sample. Okay, so the question is, what is that probability? Okay, now I'm not interested in just applying the formula here. What I want to do is appeal to your intuition, which is astounding. I found out having taught the course for this semester. Do you think it's going to be likely when I reach in there and pull out at random 4 balls that 2 of them will be black and 2 of them will be white? Do you think that's likely? And if not, you tell me what you think.
More likely than any other option.
Interesting. Well, what are my options anyhow? Let's go over them. Just a couple of them. What could it be? 3 whites and a black one, right? Or 3 blacks and a white. I mean, there's kind of a lot of options here, right? 2. Okay, so, well, how many are there? I want ones that don't work. You can have all white, right? All black. It looks like there's, I don't know what you mean by more likely than the other. So we're talking about two different cases, right? I mean, I don't know.
I'm not saying that it's going to be 50% to get white, black. I'm just saying that I think that of the options, I think it's the highest one.
It probably is, but you can gang up on you. These other cases can gang up.
Yeah,
right?
I'm doing the math right now to get the probabilities.
I don't want to remove you from your glory. So
I know.
Let me tell you you tell me what you think the answer is. I think you know the answer, but what do you think the answer is about? Give me a.
Well, I guess it's more, I feel like 10 reps to get white, black. It feels a little high. But I mean, again, I'm going to actually do the math to find out the exact number.
I bet there's a 4% chance. That's my bet.
Okay, so how do we model this? There's 2 distributions that work here, right? The first one is what? The first distribution is it's hypergeometric. We've got to know what is our success probability. What is our probability of reaching in and getting a perfect, I say a balanced hand, right? What is that probability? So we need, and then I have to use what distribution on it? Which one tells you how many reps to the first success? What distribution is that?
That's binomial.
Okay.
Wait,
careful.
No, you're right. It's geometric.
It's worried out. Okay, yeah, no, you got it right. So there's actually 2 things going on here. So I say we start
binomial.
I don't think this is binomial.
Well,
I just have to get a success probability, and that's where the hypergeometric distribution comes in.
Yeah, but success on one trial is binomial, isn't it?
No, because it said the first success. So it's different than binomial. See, but geometric is like, what is the probability that it took like 9 reps before you got your first success on the 10th, right?
Yeah, but you just said there's 2 different distributions that we have to basically.
Okay, exactly. I first need to get what's my success probability for this.
Yeah, and that's what I was saying.
That's what I have to compute,
binomial.
and that's it's hypergeometric.
What? What does that even
I'm
mean?
a little confused on it being hypergeometric because hypergeometric implies that we're going to keep going, but here we're told that the sample size is 4. There's a specific number of tries we're going for.
Right. So we first this will good question. This will first tell us what's the likelihood that on 1 rep that I get success.
Right. Yeah, that's where I'm thinking we're going.
Because if you keep going, we're putting the balls back in there. Of course, it's not like there's some memory what happened before. So let's use this as an excuse to recall the hypergeometric distribution. So, what would be the probability that this is hypergeometric now? X equals I, and let's recall that. So, I need space. I need some space. So this is 8 total. You can see that there's 8 total there. So probability, so X is hypergeometric. So probability that X equals I, and this is the sample size, size equals M. So what do we have here? So you want to get I, and darn it, I need to, you know what? I need a picture here. So there's M, drawing it. What is my sample size? It must got to be M. There must be M white and N minus M black balls, and it should be N total. Now let me get this right. So I'm taking I of the white ones, right? And then that's a sample of size N. So that means that I'm needed to take N. This is not good.
It's capital N minus M, choose lowercase n minus I,
I just forgot
the rest of them.
the sample size. The sample size is little n, not, this is, I gotta keep my n's and m's. That's little n. So, right, so, so how many, so from the black ones, this is how many black ones we have. We want to take n minus I, right? That's what you said, right? I think.
Yes.
And all possible samples, sample sizes n would be this. And capital N, choose little n. Okay. Make sure I've got my constants in order here. Okay, finally. So how do I do this now? What was my situation here? How many total did I have? So 8 total. And we have 4 white.
And 4 black.
4 black, good. So let's apply that formula. So in this case, wow, it took me a lot of struggling. I think teaching algorithms is not good for your health. Anecdotal evidence in my lifetime. Because your brain starts listening to these arguments about how algorithm, and it says, well, let's organize ourselves algorithmically, and that's not good. Okay, so what would be these? Let's get this probability that we get a balanced hand here, right? So what do we have in the bottom? We have 8, and the sample size is 4. And now M is, okay, so that's, M is, so M choose, we want 2 of these guys, 2 white ones, and then from these, so 8 minus 4 is, M, okay, what is M? So M is, you want it to, is 4. It's the number of white balls. M is 4. And then you have 8 minus 4, which is 4. Choose 4 minus 4 minus 2 is 2. Okay, wow, it took me forever to do that. But what is that number? So the success probability on one pop is what? Somebody help me. What is 4 choose 2?
6. I have that one memorized, but I have to look up 8 choose 4. Choose 4.
70 or something?
70, yeah.
So this is surprising. Now this number surprises me a little bit because we're getting dangerously close to 50%. So every time you do this, you reach in and play this game, you get close to 50% of terminating it right there. So I think that Ethan may be right that this is pretty unlikely that it's going to take that long to succeed. To get one that's balanced. In fact, we can calculate.
Sir?
Also, that's going to be. Oh, sorry.
Yes.
Can I ask a question?
Yes, absolutely. Go ahead.
So so this is the probability that after 2 trials, we get the success, or because you put
No.
I is equal to 2 in this, right?
Oh, but these are two different things. So we're going to apply the geometric distribution, but we're first going to find what the success probability is. So
Yeah, but you're saying X is equal to 2, right?
Yeah, X
Because
in
you
this
plugged
case-
in I.
X in this case is the number of white balls, I believe.
yes, I is the number of white balls. So right, it's 2
Oh, okay.
on one draw. What you see, I'm trying to compute the probability that I get 2 white balls, which means if I have exactly 2 white balls, I must have 2 black ones. So that corresponds to that situation where we're done with the experiment, right? When you get 2 whites and 2 blacks. So that's all I have to say is 2 white because the sample size is 4. Okay, so this tells me the probability that I am successful on the very first pop for the geometric. Boom! I just get it. I get 2 whites and 2 blacks. And what I'm trying to say here is it's a little bit surprising, is it not, that the success probability is so close to 50%? Because other things can happen, but it's just strange that that's why we did the problem, because it's kind of neat. So that's on 1 rep. But the problem in the book says, what's the probability that you're not successful on the first one, and on the second you're not successful? So you keep repeating all the way to the 10th, and the 10th you have your first success. So that requires the geometric distribution. Does that make any sense, or I'll stop here and wait?
It's going to be 0.1%.
That's within an order of magnitude, dude. It's pretty good. I know. Let's do it. Let's do it really quick here. So, what would be that probability? So, the geometric thing is, well, what is my success probability? What is that? Can I simplify that number? What is it? 18.
Yeah.
18 over 35 to the what?
To the 10th, right?
Well, let's see. Remember, this is you get
Or is it to the
success
9th?
on the 10th. So you want to have the fail probability. How many times you want the fail probability? You want that 9, right? And on the 10th, what do you get?
And then the success probability too, right?
Yes, which is 18 over 35. So
It's still close to being it to the 10th because it's close to 1/2.
yeah, but it'd be nice to get it exactly. You might turn out to be.
Yeah, no, I'm not saying. Yeah,
You might.
I did it approximate in my head.
Well, let's do it exact, because it might be that you're right. It turns out that you're closer than you thought. Does anybody have a calculator who can try this?
I could try.
0.0007738.
What is that? 7?
Yeah, 7738.
Okay.
So 0.07%.
Okay, so I would call this. Yeah, I would call this unlikely, very unlikely. It's like tossing a coin, and a fairly well balanced coin, with heads and tails, and it takes you to get your first tails. It takes you 10 shots. It's it's sort of unlikely. So okay, this was a good try, but let's go back to Elizabeth. Did that resolve? Did we resolve that, or are you still? Is there any issue between the two?
Well, you're saying that the probability of after 10 reps, you get a success is 0.07?
Well, no.
Percent?
Okay, that's not quite. It's the probability of having 9 fails, and then your first success on the 10th rep. So there's a history here. You know what I mean? It's like fail, and then the first success. What's the probability of that? Since they're independent, we multiply them.
So is that why it's to the power of 9?
Yes, these are your fails. Right, 1 minus success probability, that's the fail.
Cool.
So you have 9 fails in a row. Think of it as heads and tails. You have like 9 heads in a, 9 tails in a row, and then first head on the 10th. Okay, but your success probability remains the same from one trial to another. Okay, I'll slow down. I want to make sure you get this. This is two different distributions that are at work here to do this.
Real quick, so that's 1 minus 18 over 35 to the power of 9, then times 18 over 35?
Yes.
Okay, all right.
Is this what you guys got? Aim's going like this. I guess it's correct. No? Oh, you're not sure?
I gave you the number. So,
No. I could have made a logical error in this. I mean,
yeah, that's the same thing I got. Mhm.
okay, I could have made a
Seems right to
logical
me.
error. In fact, if you want to simplify this, you could do it, right? I mean, this would be what? 17 over 35 to the 9. What is it? Yeah. I mean, you could play with it a little bit to make it look more like the books. But getting back to Elizabeth, is your question? So, did we address it?
Yeah, no, I was just confused about the I, like why you put 2 and I, but you answered my question already.
Okay, good.
Because
yeah.
we're just looking at the success of, getting 2.
Exactly, because once you say you've got 2 white balls, you know for sure because the sample is size 4 that you have 2 black ones. You don't have to specify that. So that's why there's just the count of the white ones here.
So, is this the first day that we've gone over hypergeometric? Because I don't remember this before.
We did do something, but I think as Game had pointed out, the example was
Out of the room.
underwhelming. The example in the book was underwhelming that we did.
Yeah, we did it Thursday of last week.
But it was like not the problem was more about conditional probability than the use of the hypergeometric seemed like an afterthought. But in this case, it's quite interesting because something you would think is rare, to get a balanced hand, of the 4, is actually pretty common to happen. So it's like there's something not intuitive about this. At least it wasn't for me. I was shocked. I had to do this 5 times before I believed.
Well, when we talked about like binomial distribution of like something, what was it with like voting and stuff? That's
right. The chance of getting.
What I didn't expect that either then,
didn't
but
either.
now I do because now I've seen that.
Right. Yes. Yeah. This, of course, that's all related to. You've probably had enough of it, but the birthday paradox, right? That's why they call it a birthday paradox. It's just so many ways you could get a collision. That's why it surprises you, that it takes so few people before it's likely you have a collision. I forget the exact number for the regular birthday paradox. It's like 24 or something.
Nobody would 11, 12 people.
No, it's about 23 or something. But nobody would believe. Nobody believes that unless
it's very interesting.
Nobody believes it.
So what? So is there a regular geometric distribution?
I'm not sure.
It's not hyper.
Yes, there is.
What
the geometric distribution.
What's that?
The number of trials until you get a success. We just used it. So like what we just did, where we had 9 failures and then a success, that's called the geometric distribution.
Really?
Yeah.
Okay.
You needed that for the test, for the recurrence relation, right? For the expectation. That was the critical. I thought, stupid me, but I believe that was a critical piece of getting that expectation.
Professor, I thought
geometric. How does it differ from binomial?
Well, hold on a second, Ethan. Let's
Okay.
Let's Elizabeth.
No, I thought I'm changing the topic because I thought the original question that you had asked was about like how is it more likely to get half and half than the other? Like
yes, right, and we found out.
I thought they're all equally probable. I thought it's all.
Oh
no.
Good question.
It's. Or maybe I'm probably just forgetting the original question was.
Listen, guys, let's address this right now. This is an excellent thing to look at, this concept, okay? This is critical, okay? So let's do the simplest example of this phenomenon. So suppose you toss a coin twice. Now, what would be the sample space? Okay? And assume the tail and heads are equally likely, right? So this is a situation here. So if your events are both both heads, both tails, or one of each, these are not equally likely.
Shouldn't one of those be HH or no?
Both heads, that's HH.
Oh yeah. But,
No,
but
in your,
talk-
in your
Yeah,
sample
yeah.
size, you put tails twice instead of
Yeah.
heads tail or heads.
Did I?
Yeah.
Yeah.
In the sample
The
space.
sample space, yeah.
Oh, sorry. Sorry, I was looking at this and I'm saying, well, you know, okay. So the thing is, you're going to be careful how you specify the sample space because you might say, okay, I've got 3 events. I've got 1, 2, and 3. And you might say, well, I've got 3 events, so they're equally likely as all a third. That's not true. This event is 50% and these 2 are a quarter. And I suspect the same thing's happening with the hypergeometric, okay? I suspect that you don't, you know, I mean, this is a really good teaching moment here for all of us. That you know, just because the sample space, you think what it is, they may not be equally likely.
Yeah, because there's a lot of different ways to get the same number. So for numbers that are in the middle of the range, there's
Exactly.
like
So-
most ways to get it.
So in this example we did, you had what were the different things? Remember, sample size was what? Size was 4. So you could have, besides what we wanted, right? Something like that. What were the other things? You know, it's like I don't think these are equally likely. I don't know. I wasn't prepared for this, but when I write it like this, I'm saying you get 2 of each. So what I should have said is 2 of each. So 2 of each, white and black, versus what? All white. We just did 2 of each, right? What did we get for that?
50%.
Around 50. What was it? Okay, it was around. I don't know what. It wasn't
It
exactly.
was 18 over.
Yeah, 18 over 35.
Give me a number for it. I want to be precise.
18 over 35.
No, but I want decimals.
0.5,
Oh,
0.5142.
0.51. Okay. Now, this getting this all white. I mean, we could. We have to calculate that, right? What is it? It's what's in the denominator. 70. I'm trying to calculate. Was it 70 in the bottom, and then to get all white?
36 on top.
There's just how many ways when you grab 4, they all be white. It seems like it's
One.
kind of small, right? These things are quite different. You know, I mean, a particular string of them might be the same probability. It's just different. This is why you have this distribution. What else is possible for you to get? You can get 1 white and 3 black. So what is that probability? Well, it's a lot more than all white, but it's some. You know, I don't think it's 51%. So it's sort of like it's an assumption we make sometimes that the sample space probabilities are equal, but there's not. In this case, it's not. Why is that so? I think it has to do with if there's no replacement. That may have something to do with it. You know, the driver behind it.
Well, it is with replacement though.
No.
We are replacing.
No.
Are we putting them back in the?
No, okay, you do. Okay, 1 rep is you reach in and you grab 4 of them, right? Let me draw a picture for that. So 1 rep, you've got eight of them in here, right? And some of them are okay. So one rep would be okay. I choose.
Yeah, we
4.
replace them each rep, but we don't replace
Right
them
after I
individually.
check, and I look at it and I say, are half of them white and half black? If so, I'm done. We stop. If it's anything else, we put those balls back in and stir the pot. Am I stirring the pot? No, we randomize, and then we take another subset of 4. I can't do this. When I used to play the piano, I could, but I grabbed 4 of them. So the reps are the repetition of the experiment. The experiment is to take 4 randomly. Does that make any sense? But success probability is 51% on a given draw of 4, that we're going to get a balanced hand, 2 white and 2 black. If we don't, we put it back in and we do it again. The question is, what is the likelihood, the probability that we had to do it 10 times before we hit that, 9 times before, after that, we hit the first balanced draw? Okay, I'll slow down. I mean, I want to make sure you get this. I don't want anybody to get. Does this make any sense? It's like a 2-stage problem. On a given draw, we want to know what is the probability that we get 2 whites and 2 blacks? And the second part of the problem is, with what probability does this process, we repeat it until we're successful? Does it take 10 draws?
So if we wanted to calculate the probability of 1 white and 3 blacks, we would put it into the hypergeometric equation.
Yes.
Put I is equal to 1 or
We should
something.
do
Or
it.
Yeah.
We should do
yeah.
that.
Okay. Well, I'm just confused. We got 18/35 through the hypergeometric
I believe so.
formula, right?
so.
Yeah. Okay.
What was in the top? It was 36/70, right?
Yeah.
Right, and that's 18/35. Right, exactly. But I mean, you have a good question. What would happen? Let's calculate. What if you get 1 white and 3 blacks? What would be that probability? I mean, I'm just making sure you understand the formula. So let's check it out. So 1 white and 3 blacks. So what do we? So x is hypergeometric, and you want the probability that x equals what? X is the count of the what?
White balls, I guess.
Right. Are you good with that, Elizabeth?
Yes.
So you counted the white ones, and you only have 1 white one. So now I need some help here. The general formula. Let me get the bottom thing right. There are 8 balls altogether. I'm selecting 4, right? That's all possibilities. Now, how many white ones do we have altogether? There's 4. And
You were picking 1.
we're picking 1. But then the other ones have to be black ones, right?
Yeah. So there's 4 black
So-
balls, and we're picking 3 black.
Okay, so the formula goes like what here? So there's
It was the big N minus whatever was called.
There's 4. It seems to me there's 4. It seems to me it's
So
this.
4.
Okay, stop me if I'm wrong, but it looks like 16.
And that's 4 times. Let's see.
Right, because I have a reservoir. This is how many ways we could choose: 1 white ball and 3 black balls. So there's 4 total black ones. That's what's a given. That was given. So what is this equal to?
Yeah, 16/70. So yeah.
Okay, and that, what is that as a decimal? Somebody can do it.
0.228. 0.23.
So this is a much less likely result of a draw than it would be to get a balanced one. I mean, this is sort of the issue here, right? It makes it unintuitive. So this is less likely. You say, well, okay, so getting a perfect balance, that's as Aim was saying, there's more ways that could occur.
Oh wow! You know what I just realized? This kind of explains why taking a decent sized sample of, taking a sample of a distribution tends to reflect the actual distribution. This would be like the reason for that.
Okay. Let's be careful here. Right. That's a true. This is like, it's true, yes, but
That's cool.
there's certain properties that have to be had here, you guys, before you understand the profundity of that statement. You need to have you need to have the population thoroughly mixed. Okay, you have to really have a random sample to be making those kind of statements. Okay. And like if and I think what Ethan is referring to is if you have a close election coming up, right? Say a presidential election. So let's say that it's super close. It's essentially 50-50. as was the case in Gore and Bush, right, or something like in Florida. So the question is, how big of a sample do you need to select randomly to be able to see if one of these is a little bit bigger than the other? You know, this one's a little bit less. 50.001 and 49.900. How big of a sample? In other words, it's a close election. There's a lot of people that are going to vote. How many people do you have to sample, call them up and say, who are you going to vote for before you're confident that you know who's going to win? This was something that was discovered quite a while ago. I think it was in the 1800s, okay, that they discovered this. It turns out that the population size don't matter. It doesn't matter. If your sample is random, you don't need that large of a sample to find out who's going to win, okay? In fact, for the U.S. Election, when it's a tight race, they need about 1,200 to call 1,200 people, as long as it's done randomly.
Wow. So it's probably like you just need enough of a sample size that where like one single individual will make up less than the delta.
We have to be careful. Okay, remember, this is statistics. This is not absolute. You're going to make the correct prediction 90% of the time. You see, that's where it's not like, oh, we know for sure now. You know, the only way to know for sure is to sample everybody. Okay, you know, like, but if your margin of error, if you're allowing that, you know, you're allowing it to say we're going to be right 90% of the time, you don't need a very large sample. This is
so cool.
And if you're playing a game where you're right 9 out of 10 times, you're never going to be wrong. Especially because there's only an election every 4 years. Okay, so it's this was discovered. You guys should, you know, you should look. What you should do is Wikipedia say polling history of polls, right? History of polls, and I was shocked when I went in there and realized, oh, they knew about this. They discovered it in 18 something. You know, they got wind of this thing pretty early. And again, the hard thing is, how do you select a random sample? This is difficult because if it's like in a presidential election, do you just sample everybody? Some British guy bet 5 million, or he gambled on what? That Trump would win. Good, I'm glad he lost. No, I'm going to get in trouble. I'm going to get in trouble. Don't turn me in, you guys. I'm old and tired. But no, I remember. I'm sorry, you guys. I was in young TA at USC. And I quoted, I was a TA, right? So I quoted an article from Scientific American. And lo and behold, somebody popped up, stood up in the class when I was doing my TA thing and said, don't trust that. Don't trust it's a liberal pack of lies or something. Don't read that, you know, Scientific American thing. Oh my God, man, you know. You know, oh well. What was I going to say? It's small sample, you know. Small, okay, how do you get a random sample? That's very, very tricky, okay? That's the thing that requires finesse. If you take your sample from the same small town in Idaho, that ain't a random sample of all the voters, right? So what they do is they don't just spray, you know, go with area codes calling up people. No, you do something called a stratified random sample. So they identify voters as strata, you know, as groups in the country, and you take a certain number from each strata. This is how it works. You probably know this anyhow, you guys. You learned in high school or something, but that's how it works.
You take a number from each strata, like
a set number, right?
Like basically proportional to the amount of influence that they're actually going to have.
So. This is how it's done. This is because they know that they know that in certain regions the voters are similar, so there's no need to take a huge sample from a place where everybody's voting the same, you know, right? So you know you don't need to, and I'm talking about a close election. So you know it's just it's a shock to some people that say, really, 1,200 people is all you need to know.
That's
you know how they're
really
going to vote. You can look. It's worked every time except for Dewey. I think that was a problem when they did Dewey versus. Anybody know who Dewey was? A candidate who was pronounced the winner, only to find out the next morning it was the other guy. Mm-hmm. And they made a mistake, and they owned up to it. The pollsters, the statisticians, they owned up to it. They you know, they fixed whatever problem it was that led to that embarrassment. Okay, guys, let's. Am I running out of time, or what is my situation? When is this class supposed? No, we have time, right?
We've got 20 minutes.
Yeah, 20 minutes, and I was going to do some easy stuff, and I don't know. I'm just. Yeah, I'm torn between should I do easy problems for the book examples so they all feel good, or should I pounce on the hard, the hard thing?
I had a quick question about like concepts.
Yeah.
So what exactly is the difference between a hypergeometric distribution and the binomial one? I feel like they're related.
They are related, but
basically like the same thing. But is it one that is multiplied by like an additional term or something?
Okay. The short answer, the short answer, Ethan. When you do the hypergeometric, you've got the total number of balls, right? What is it's n, right?
Right. The big N.
You earned it, right? You earned it. No, I'm sorry. And if n is really big, and you take in a small sample, suppose you're doing a sample size of 100.
Okay.
So what would you call the sample size? Was that m or n? No, I can't remember. I think it was n. So n is the sample size, and say that that's 100. I mean, this is huge here. It's big, right?
Okay.
Now, when if you want to calculate the probability that you get 4 black balls or something, excuse me, if 60 black balls or something like that.
Okay.
In a draw, if n is huge, the probability of hitting the probability of selecting a black ball, you see, is not going to decrease very much if n is huge, right? So the fact that the hypergeometric is without replacement, right? Sample without replacement. But if it can be approximated by a sample with replacement. I mean, you can assume that the probability of a black one don't change at all, essentially. Okay.
Okay.
So it sort of has this. I don't know. I don't want to overuse the word, but sort of an asymptotic sort of approximation. Where you say, okay, just do it binomial. Just think of it as binomial. It turns out that when you're computing the mean, you can basically take the binomial mean. Okay, I mean it's
okay. So you're wait. Remind me what binomial is. I don't understand.
Okay, binomial is every trial has the same probability of success.
Oh, really?
Now, sure, right. I mean, like you're tossing a coin. The coin doesn't remember that it came up heads 5 times in a row, and now it's time to do tails. Right? Those tosses.
I believe that. I know. I can't remember. I couldn't remember.
It has the same probability, right?
No, I understand that. I just want to understand the definition of what a freaking binomial distribution is.
Okay. It's just the count of successes in independent trials where the probability of success for each trial is p.
Okay.
Okay. If you're reading the book, which I don't know that you guys are doing, but if you're going to go actuary, you should know that if the binomial distribution, if you allow the probability of success to fluctuate just a little bit, in small amounts, then the Poisson distribution still is a good approximation. So it's binomial-like, right? So to say that it has to have the same probability of success exactly is not intellectual honesty on my part. But that's the way theoretically it's set up. So when you're doing a hypergeometric situation, you're pulling out, if your sample size is small compared to this ocean of balls in that urn, then you basically don't change its binomial type. It's binomial in nature. Your success probability is not changed. Everybody clear on this? I'm sorry.
So can you write down the formula for the binomial again? Because I
better do. Okay, I'm just afraid of. Can you hang after the class a little bit?
Yeah, that's fine. I don't want to diverge too much.
Dewey defeats Truman. Yeah, if you have a newspaper with that headline, it's probably worth some cash. Okay, so I've forgotten where I was. I was doing. Oh, yes, I was going to, okay. Just, this is a weird lecture, but here's another thing about with the binomial. Okay, so suppose you toss a coin 10,000 times. How long would it take you to do that?
Yep.
And let me look at the numerical number of heads that you got. Suppose you get 5,800 heads. Okay.
That's
The
not a
question
fair
here is it reasonable to assume, is it at all reasonable to assume that this coin is fair?
No.
Is it reasonable to assume this coin is fair? Question mark, right? Okay, you might say, why in the hell are you doing this, Dai? Because out of that chapter, this seems like something from chapter 4. We got to do continuous things. Well, I'll ask you this question: why does this appear in this part of the book? Why is this in chapter 5? Give me the quick answer. Somebody else did, so I haven't heard from AIM. Why is this in chapter 5?
I mean, I think this is going, in 341, we would, what's it called? You would do a test where you make a hypothesis.
Oh,
and,
yeah.
It feels kind of like that. I don't know.
It feels formal, and I'm not.
Okay.
I'm not dressed formally, right? I'm dressed so formal. Let's get that formal stuff out of the office. We'll just do a clean sweep. I think I need to do a clean sweep. Anyhow, so she's right. She's right. That test is what it's saying is. The question becomes, they reframe the question a little bit. They say, well, how likely is it to get a result this extreme? And let me underline what the result was. You get a result of 5,800 or more extreme, which means more heads, right? What is the probability of, but she's saying, what is the null hypothesis? So what is the assumption when you set up this test? You're assuming that this is a fair coin. If it was a fair coin, what is the probability that you get 5,800 or more heads? So I taught this in GE stats, right? And somebody says, well, what if you got 1 million heads? And I'm saying, dude, you're not reading you're reading the problem. How many times we tossed it 10,000 times, okay? You guys, you become professors yourself, and you're going to have these issues, And the worst issue I ever had, sorry, I'm digressing, was I had 1 minus p in a formula, and p was a half, and I just put down a half instead of 1 minus a half, and the gentleman in the class said, that's not right. And I said, what's not right? He says, 1 minus a half is not a half. And I said, why not? He says, you can't take back what you took away. I was like, oh my God, this is college, man. And so I drew a pie, and half of the pie was gone, and there's a half left, and he still wasn't convinced. I said, use the calculator. 1 minus 0.5 is 0.5, and he just shut up after that. But anyhow, let's look at this situation. And believe it or not, some people have actually, prior to the time of computers, they actually did toss coins to find out if they were fair by doing this. What do you think? What is your intuition? You did it 10,000 times. What do you think is going to happen? If you got 5,800 heads, what is the probability of getting 5,800 or more? What is your feeling about this?
It's going to be pretty unlikely, especially given what you said about, sample size of 12,000 to call a close election. So,
okay, but let's use what we were just talking about, Ethan. So, what is the distribution that we need to use here? Each toss is independent. So again, we were talking about
it's binomial, right?
It's binomial what? It's binomial. By the way, this notation of B, the big B and the NP, This is CLRS talking. Engineers know how to present stuff the best way. I don't know. They're just efficient. Mathematicians love to make it complicated and pretty and aesthetic, and pleasing, confusing and stuff. But the engineers, they're tired. That doesn't do anything for them. They want the problem clear, the statement clear, the answer clear, and how they did it, they don't tell anybody. But it just
I can vouch for that.
So what is this? This is binomial 10,000. And this is, here's the thing AIM is talking about. What is the null hypothesis? The null hypothesis is the coin is fair. And then you got to state that before you collect any data. Otherwise, that's called fudging data. you change the test, to make your data seem significant. I mean, that happens a lot. But so in advance, we say the coin is fair. And fair means with what probability does it come up heads?
Yeah.
What do I need to calculate to answer this question? What do I need to calculate?
So probability of x greater than or equal to 5.
Well, let's be precise here.
5,800.
Let's do like the engineers do. Okay, we're gonna be careful. we don't have how many total tosses do we have here?
So 10,000 greater than or equal to x greater than or equal to 5,800.
So we want x.
Yeah, between
less than or equal to
those two.
10,000, right? We need to calculate that. Now look, there's a problem here. That's a heck of a lot of binomial coefficients, and they're already, I can't remember what 8 choose 4 is. So it's like, oh my gosh, what am I going to do here?
Yeah.
This is where, if you're on the math side of the spectrum, you say we need to get an approximation here. We need to find out. You say it's like the normal curve. Like almost everybody in my class has seen the normal curve at some time. Okay, they're sort of familiar with basic stuff of statistics. So we need to get that approximation. And the question is, what is the approximation? And not even how good is it, just what is that approximation? And I should give that to you because this is rather interesting things. So the approximation goes like this. So the probability of so x it will be the count of successes or the heads in n trials. So I argue a little bit with the way this is presented in the book. They use SN, S for sum. We've never used S for sum in the book prior to this. They always use X. So this is very confusing. Now there's a new symbol for what they should have, if they wanted to use for sum, like the count of the heads, they should use S from the beginning. They didn't. So X minus, now you're going to do some, if you've studied, if you've taken pre-calc and you do graphs, you know about translations and scalings of graph, right? It doesn't change the nature of it. Like a parabola is a parabola, but you can translate it left and right, or you can elongate it or compactify it by a scale factor, okay? So what we're doing here is just scale factors. We're not changing the nature of x over the square root of np times 1 minus p. And this, we're saying it's the probability that after you scaled x like this, scaled and translated, it lands in that range, goes to, as n tends to infinity, goes to what? Well, you can calculate this. It means that this is looking like, the distribution is looking like a normal curve. If you're taking a standardized z, z is the normal, standard normal, you want to know between A and B, how do you do that? And let me withdraw for a second and draw a picture in case you haven't done this before. So if you have a normal curve, a standard normal, the center of it's at 0. That's very convenient. It's nice. So of course, I didn't draw it that way. The center's at 0, and this is your standard deviation. It's doing a sloppy job drawing. Something like this. And this is the standard normal. Now, if you want to get, if you want to find the probability of the standard, this usually gives us not x, but they call it z. if you want to know the probability that Z is between A and B, how do you do that? Well,
Wait, what's Z stand for?
standard normal random variable. It has the bell, but it's got two parameters. It's got a center, the mean is 0, and it's got this measure. It's just called the standard deviation. This measure of how of its variance. Okay, whether it's really spread out or it's Gothic.
Right.
Okay, now if this was, let's change it up. So if this was A here, and say this is B, how would I find the area between A and B? How would I find it? Because what you have to do, this is the proportion of the observations that lie in this region. This is continuous random variable here. Well,
Take the integral and find the area under the curve.
you could integrate it, but it's a mess. It's a messy integral. What they do is they have tables. It's sort of preset here, where you find out all the. It's called the CDF. Everything up to this point. Okay, up to this point. Cumulative distribution function. Everything up to this point, and then you subtract off everything up to this point. So this gets canceled out, and then what you have left is this. So the way you express this, we will have to do it. It's part of our part of the SLOs in this course. We can't escape it. We have to learn how to use tables. So they use this phi, capital Phi, in capital Phi, this is the CDF for Z here. So let me just test it. If you took phi of 0, what would phi of 0 be? Let me just test you if you're following me. It would be everything from the left up to 0. So if this is a probability distribution, a probability density function. So when you integrate, as the name says, from all the way to the left to the middle, you expect to get how much?
Half.
Is everybody clear on that? That would be 50% or a half. 0.5. People tend to use decimals because the table is set in decimals, okay? We have to go through this process. So what I'm saying is the table is available to us. It's actually not in an appendix. It's interior to the book. The author considers it very important for you guys to be able to use the table. So for this formula, it turns out, I do this in blue, so maybe it will stand out, that the answer to this is phi of B minus phi of A. Not the answer, but it's heading towards, as n gets large, this quantity, this probability here, is heading towards this. So essentially what that means is this guy here, this random variable, this translated x. X was binomial, right? And we just did a little translation, a little stretch to it. That thing is normal. So
what we do with NP, and those terms there is normalize it so that everything falls within like 1.
Well, this thing, okay, just be careful. So this is okay. I'm sorry, this is the x from binomial. So x is binomial NP. Hopefully I'm not in the washout. But that's what that is. So there's really an implicit. This is the count of successes. So it's implicitly there's an n there. I don't want to put that n there. Okay, I don't like it. I do this. My previous life when I was doing research in functional analysis, we would never put an n there. Okay, we know what that is, but this is
okay.
So so in other words, this approximation becomes better when n is large. Okay. And in fact, as I've written it a couple of times, but this is a rule of thumb. If you have this quantity greater than or equal to 10, then the approximation is safe. Okay.
Okay. I feel like I understand it a bit better. Thanks. So So, but our scaling factors and things that we've got going on there, we're subtracting 500 from it in this case.
Oh, you're actually doing the problem. Wait a second. You're doing the problem with the heads, right? You're actually doing it.
Yeah.
Right. That was my next step. No. We need to do it. The next step is, hey, let's find out how likely it is to get 5,800.
Yeah, I really want to find out.
More heads. I mean, this is like a quest, right? And probably killing some people because it's too. This is theoretical. This is convergence, and stuff. And
no, it's cool.
But this is the neat thing because it gives you another reason why the normal distribution is at the center of everything. It's in the center of how you prove things.
So okay. Quick question. So I'm just trying to get at that minus NP and divided by the square root of that. That basically always stretches and scales this.
Well, that's true for any function, right?
Into a standard normal, basically.
Okay, look. I mean, this is not complicated. That part's not complicated, right? The part's not complicated because suppose you had. Let's take a really simple case. Suppose I had this box distribution, okay, the uniform distribution, right? And it's this is minus 10, the center of it. Mm-hmm. It would be nicer, wouldn't it, if the center was at 0, right? So what would you do if X was uniform? I don't know what it is. I need to move this over. So what would it have been originally?
So you subtract basically half of it.
Yeah, minus 10.5.
Half of the distribution.
10.5. So now it's okay. So if it was, so this is minus 10.5 to 10.5. Okay, like that. So this, but I like things to be centered, right? So what I have to add?
Subtract the middle of the distribution.
Yeah.
Okay.
I want to move that middle over to. Oh, I see. You might want to go from 0 to 1, 2, but in general, it's good to. Symmetry is a good thing. So move it over. Move this.
Yeah. From negative.
You're not changing.
It's right in the middle. Negative on the left, positive on the right.
Yeah, you're not changing anything. You're just making it. This is what's happening here. You're centering it.
Yeah. Okay. And then the one below that. What's going on there?
So I don't know if you remember, but the variance of a binomial is NP. We did it. Is this. So
variance?
The standard deviation is the square root of this.
The standard deviation is the square root of that.
Yeah.
And so then every unit is a standard deviation?
Yes.
Right. On the standard normal?
Yes, right. Standard normal, right.
Okay.
0, 1, 2. Okay. So let me draw you another.
Okay, now I get it.
We're approximating our situation is we're approximating with a normal curve, right?
Mm-hmm.
Now, it's not only a normal curve, it's a standardized normal curve. So that means the center is at 0 and that's
yay. Easy numbers.
This is 2. This is 3. The normal curve is known for not just having the bell shape, but having those arms come down really fast and spread out. So there's not much mass in the distribution in the arms as they go out.
It reminds me of the logo for Spectre, the octopus.
Okay, so it comes down real fast. So my question to you is, the problem we have, which got erased, but what was the problem? How many heads? You had 10,000 tosses, right? And how many heads? 5,800? Well, I forgot what it was. 5,600 or 58?
5,800.
5,800 heads. Okay, where do you think that result, after you've normalized, where one standard deviation is here, from here to here, that's approximately, within one standard deviation is approximately 68% of the observations. So where do you think, how many standard deviations out do you think this result is?
I think it's pretty far.
Yeah, it turns out.
I bet it's like 3 or 4.
Statisticians are very good at giving you examples of something that's a certain number of standard deviations from the mean. Like Shaquille O'Neal, the famous NBA player, his height is 7'2" or something like that. That's something like 6 standard deviations over to the right from a normal adult height. So I mean, they have these examples, like how likely is it to land, in that range. You know,
Mhm.
7'2" or higher. It's really unlikely.
That's pretty cool.
I've actually seen him live one place, and it looked like a moving mountain. Smooth. He was an athlete. He was moving really smoothly, but it's like a mountain was moving through the masses. Okay, so let me check my time.
Oh, I think we're like over by
Oh
quite a
crap!
bit.
Because what I wanted to do was okay, you guys, I wanted to fill in this information, calculate this, use the table,
Yeah, I was gonna
and
say,
find
like, how
out
do
what,
we
find
how
out
do
what the
we
probability
solve it?
is. And I don't want to spill the beans and tell you what the answer. I want you to do it yourself. Is this?
I don't know how to continue with it.
Can you guys? Can you promise me to look into it? I mean, this is a fundamental problem here. Can you try it? Basically, that's what I'm asking you. So you want the range? You want to start it with 1500 to infinity. So this would be. Okay, yeah. So you're starting at 1500 and you're going to not infinity, but for purposes of rounding off, you can put infinity there. You don't have to put 10,000. So find out what this is, what this probability is, and it'll be unmistakable. Your answer will be unmistakable when you get it. But you have to, you've got to take this result 1500 and then you make these. It's called the normalization of this raw data. X is the
All right. Well, so what's A equal to, for example? Or what's B equal to? So B
Yeah,
is going to
okay, let's do it.
correspond to 10,000, right?
Okay, I'm probably
And then-
gonna get.
So what is it equal to?
Very
Is it
angry, but you
10,000 or
want-
is it like 10,000 scaled?
You want like this, right? You're gonna do it like this.
So
10,000
we basically have to do the same transformations to A and B.
Right, exactly right. So it's
Oh, okay. Now I get it.
minus this NP. Well, you already told me if it's a if it's a fair coin, what is that?
So
5,000.
it was 10,000 times 1/2. So
Right, exactly.
5,000.
And now I'm gonna really test your powers of arithmetic, Ethan.
yeah,
What is
they're not
the
that
bottom?
good.
What is this?
I don't know. Wait, 1 minus P is also 1/2.
Yeah. What's
except-
NP? What's
Not
NP?
according to that one guy, but and then it's square root. So we have 1/2 times the square root of 5,000, which is
You did something wrong. What's NP?
no, it's equivalent to, if I did it right. Well,
No,
because I separated it out. I'm like square root of n times
No, don't do it that way. What's NP?
p.
What's
Well,
NP?
because p and 1 minus p are the same, so I just did that automatically in my head.
Because NP you already calculated. What was it?
Yeah, we did already calculate it.
5,000.
5,000. Oh, I was thinking 10,000. Ah, damn it. Fuck.
You get it.
Wait, 2 to the 5th is 32.
Oh my gosh, we've gone over. I'm gonna get fired.
I think the bottom is 16.
No. What's
50, isn't it?
Wait,
What's
The square
no.
root of 2,500.
It's 50, right?
Yeah.
Right.
Square
Right.
root of 2,500 is 50. So that's the standard deviation.
Right.
Wait, what's 2,500? I'm lost.
It's 1/2 of 5,000. Because n times p is 5,000.
Right.
The 10,000 times
Oh, yeah.
1/2 is 5,000. And then 1 minus p is 1/2.
Right.
I told you I can't do
What's the
it.
square root?
Yeah.
What's the square
Oh.
root? So what's the square root of 2,500?
Yeah.
I'm using a calculator, so you're using your head probably, so that's probably why.
Right, and that's old school. Like fistful of 50s is how many 50s? It's 50 50s. Huh? So
Why is it 50/50s? I can't fit 50 bills in my fist. That's like a lot.
but this was a big gangster guy, right? This guy's got a, you know what I mean? The joke. It's an old joke. The one you see is a 50, right? All the others are single dollars. Or single. Anyhow, it's
$99.
50. So what is this? This is the probability that what? 800 over 50. What is 800 over 50?
16. So we're asking about something that's 16 standard deviations away.
Holy
16.
shit.
Thank you. Thank you, Aim. You're back online, even though we're way out of line here with the time. But I appreciate that. Basically, the probability is zero. It's zero. I mean, unless
Holy
you're doing
crap.
astronomical calculations where, you know what I mean? Small numbers mean something, right? Like 1% of the speed of light is, you're moving fast. If you can do 1% of the speed of light, if you can do 0.01 c, you're quite a sprinter. But if it's normal life, we're not talking about astronomical calculations. This is not going to happen. In that range, that whole range, it don't happen. It just doesn't happen. Thank you, Edwin. I don't know. I'm sorry, but can you guys do this for me? Can you look this weekend? Can you go through this again and
Yeah.
make sure that you understand? Because this is the first example of a convergence theorem in this class. This is critical stuff. Okay, this is your higher level math, whatever. This is higher level, and they don't in calculus like.
Wait, but we didn't prove that it converges. We just used the fact that the binomial converges to the normal.
Exactly, but the fact is, okay, you're right. We didn't prove anything, but n is big, right? It's 10,000.
I'm convinced.
So when it's that big, you can try this on a. Well, this was a bad example, but I mean, you could use a binomial. I did that, by the way, on my cell phone. I just used a binomial calculator on the web. You got the exact value, but this is zero. The answer is zero. But other cases, it's not going to be zero. And when you have n equals 10,000 and p reasonable, you know what I mean? Like not like zero, then this approximation is darn good. Okay.
That's pretty cool.
Why is it good? Well, look at it. The book has some examples that show the binomial distribution, and they superimpose a normal density over that. It's really good.
Wow.
Okay, guys, I'm sorry. I get excited and go over. It's just it's a weakness I have.
Got another class to go to, so see you next week.
Well, thank you for showing up. I really appreciate it.
Yeah, this was pretty interesting. Thank you for explaining for me too.
Well, okay. Well, thanks for putting up with my. People say I rabbit hop, well, just a huge lot of hops, hop, skip, and a jump. Except for just hops, no jumps and maybe some stumbles. But this is anything. Anytime you have a convergence theorem, it's interesting.
Yeah, this
That's
is pretty cool.
All right.
All right, see ya.
See you guys.